and welcome. Now we're going to start off this exciting project with the first build, and that is going to be the power supply part, which of course makes sense to build that first, right? So I've drawn up a circuit diagram or a schematic of the power supply which I want, and with how I want it in my electronics book. Which my friend, when he saw it, he says, "You got a Star Trek book," just because it's got a galaxy. Anyway, so let's open my Star Trek book then. So here I've designed for myself an audio PSU, which uses a toroidal transformer. Freaking try saying that in the morning 10 times quick. It has 4 outputs. I mean, the two 12-volt DC outputs are not really needed. You can just use one, but since this has got 2 coils, let's just make use of the freaking second one as well. Isolate certain things. Anyway, basically I need DC 5 volts, DC 12 volts, and AC 12 volts. AC 12 volts simply for the incandescent bulbs, which you will be on the VU coil meter display. Apparently I've heard incandescent light bulbs last longer on AC as opposed to DC. Unlike LEDs, which are the total other way around, they won't last long on AC but last long on DC. So it's a basic 240 volt to 12 volt transformer. This is it's 2 coils. So what I did was, what I'm going to do is tie them together so it just ends up being a 240 volt one. And yeah, you get 12 volt AC out of 2 coils. Then you have a full wave rectifier for each, which converts the AC into DC. And then you have smoothing capacitors and reservoir capacitors here. And then you have that capacitor there, the bipolar capacitor, which filters out, any sort of high frequency noise or anything like this. Actually, that reminds me. Now, when I was replacing capacitors in the beep, a commenter asked me, don't you have to worry about the polarity when it comes to capacitors, which way around they go? Well, yes and no. It's 2 different types of capacitors. You get the electrolytics, which more often than not are polarized, so you have to look for the marking for the negative and the positive. However, you get some which they can go anyway. They're what we call bipolar capacitors. Now, don't be fooled by that, because electrolytics do exist that are also bipolar, like this one. You can put it in either way around. They tend to be a little bit more expensive. So yeah, do check your capacitors to see if they're polarized or not. And on here, you just have a regulator circuit, 7805, our good old friend. There's not going to be that much load on it, so it's not going to get that hot. But yeah, 7805 takes it down to 5 volts DC, and that's purely for the SIDBoomBox. Now, those of you who are not so aware of electronics, of course you will have seen something like this when you open a computer out, or a cassette player out, or hi-fi, or anything like this, a transformer. Now, this is the standard transformer, which is the iconic image which everyone recognizes as a transformer. It has a primary coil and a secondary coil. You put 240 volts or 115 in there, and you get out 9 volts, 12 volts, however many windings it has. Now, this is called an EI transformer, and I'll tell you why it's called an EI in a little while. I've decided not to use an EI transformer. Instead, I decided to use a toroidal transformer. Now, why have I decided to use a toroidal? Is it because of the nice, interesting shape? Well, that's part of it, but that's not the reason why. Now, each of these has advantages and disadvantages, though most of the advantages are in the toroidal one. So the advantages of a toroidal: less noise, less interference, more efficiency, and a nice, interesting shape. And the advantages of this is that it's actually cheaper. The mounting is easier on that than this. Other than this being cheaper and having a square shape, toroidal transformers are actually superior. Simple as. So I'm needing my trusty whiteboard to explain a few things, and also my cassette recorder. I couldn't resist. Now, first of all, why is this called an EI transformer? Wow, that's to do with the shape of it actually. Now you see the shape of this transformer is like that, right? Now I have the coil winding here, which is around the center part. Now let's say the yellow is the primary coil, which, you know, the 240 volts or 115, however many, goes into that. And then you have the secondary coil, which I'll do in orange, which is like, you know, another winding on top of that. You know, they just wound. They're completely separate coils. They're not electrically, you know, joined together at all. Then you have the secondary coil here, which, you know, it has your 12 volts out or however many. And the structure of it is actually closed by this. It's got this, you know, welded together or joined together or how, whatever. So that's an EI. That's why it's called an EI transformer. Now if you look closely at this, you can actually see the join here. Now of course these joins here affect how the transformer works. So, you know, they cause some inefficiency in this. So yeah, that is a disadvantage of one of the disadvantages of the EI transformer. Now a toroidal transformer, why it's called a toroidal transformer should be obvious, because it's a toroid. This donut or bagel shape is a toroid. Now this, as you can see, has windings all around. So, you know, you have the primary and the secondary coil windings all around, and then you have, you know, the secondary on top of that, or whichever way around. Now transformers work via electromagnetism. So with magnets you get flux lines, which are, you know, the magnetic field. Now the green lines here are actually flux lines. So, you know, that's the magnetic flux. So that's what basically would be the invisible lines that you can that you cannot see. Almost said invisible lines that you can't see. Invisible lines that you cannot see when the transformer is on, right? Now can you see these parts here, which, you know, the flux is on the outside and the inside, where it's, you know, the outside of the ferrite core. Now that is leakage. That's what makes the transformer not be so efficient. And this creates further problems, these joins here, that creates further leakage. Now another disadvantage to the EI is if you got it in audio circuits or you have it in radio circuits, or, you know, so forth, if you've got circuitry around close by here, you know, you got some sensitive circuitry close by, looks like a face already. Didn't mean for it to. Anyway. He looks like a very happy circuit. Now if you have some circuitry close by, it will actually interfere and cause some, you know, noise in the circuit. You'll be able to, you know, you can hear a hum or something like this. I've had that in my old hi-fi system, the way it was set out. You can hear the transformer hum. I did kind of wonder what the heck it was last night, because I was listening to it in the dark through headphones, as I do sometimes. And of course, I'm guessing that this is going to react to it, because this is obviously a direct drive. You know, it's just, there's no belt drive, it's just completely magnetic. That's all it is, which, as you can see, that's like an electromagnet. This is the other part of the magnet. Now I had that in an old hi-fi setup, I had that issue. You could hear hum through the speakers. And now that's the issue with these EI transformers. Now the toroidal shape is actually more interesting in the sense that it actually flows more with the flux lines. You will get flux lines which are mostly contained within the toroid itself, which is ideal, what we want. You will get, you know, some leakage. The flux lines come out and from the underneath and, you know, like this, but it's more or less the same shape as the toroid itself. So you do get some leakage, but definitely nowhere near as much leakage as you get here. So you get more efficiency in here, and, you know, there's no freaking this is no flex line going like this. Less likely to interfere with, you know, circuit dude here. I drew him differently, but okay. He's just more chilled out now. So there's less noise, more efficiency. However, the problem with, you know, these, the toroid, is that they're just expensive. Simple, and that is because these are easier to manufacture. Now you can, you know, just disassemble this, disassemble the, take the I off the E, and then, you know, just mass wind freaking coils and stick them in and stick the E on, I mean the I on the E, and then, you know, there you go. Now in this one, obviously the toroid is, you know, one shape, the actual iron core is one round piece. And to wind this, you cannot just mass wind it. It's so much harder. I think these are even wound by hand, if I'm not correct. I'm not sure how these are wound. But yeah, it's more of an effort to wind these. So these tend to cost a lot more, but they are superior. And these are commonly used in hi-fi equipment or radio equipment and stuff that is, you know, sensitive to noise or anything like this. Now let's plug this into the mains and have a little fun with it. Okay, so safety first, and what I've built for myself is a very simple, you know, dim bulb tester, which all it is just like an incandescent bulb, which is in series with the main circuit. And what this tends to do is just limit the current. So, you know, it's also an indicator of if there is a fail or a short, like if a power supply is shorting completely and, you know, it's gonna fail catastrophically. It will protect that, it will protect the circuitry and or wherever you've connected to this, and the bulb will light up. You know, it'll take all the current. And yes, the bulb being ever ready is actually coincidence. I didn't mean to buy an ever ready bulb, but hey, I seem to be attracting ever ready into my life. Now, many of you, I'm sure, have noticed that throughout my channel, in my videos, I use a lot of Euro plugs and Schuko plugs. There is a reason for that. I have a lot of appliances from Europe and the Middle East, so, you know, that's a lot of plugs to change, but to be honest, I don't even want to change them because I kind of like using Euro and Schuko plugs also. You know, it's nostalgic for me. So yeah, I'll just stick with two systems. I don't mind having adapters. It's kind of cool. But yeah, here is a basic UK plug with a switch on it and a pilot light. I've also made a little adapter for mains and, you know, the connector here so I could just link up anything which I want to test that's mains. So I can just... Here we go. Now with regards to this dim bulb tester, I have a 60 watt incandescent bulb in here, right? Now if you're powering anything, if the load is less than 60 watts, then this shouldn't really light up. It should just allow the current through, and if there's a short, then that will light up and take all the current, you know, so that whatever the load is does not get damaged. Now, if you put something over 60 watts in, it will lower the voltage even of what you're putting in, and, you know, that'll light up. So what you just got to do is just put a high wattage bulb in. You know, if you're testing something that's 100 watts, you got to put like a 100 watt bulb in or a 150 watt bulb in, something like this. For something like Signor Sanyo, you put that in, it's not going to be 60 watts. I don't want to get a copyright strike. My 80s cassette. Alright, so that will be, that's fine. You know, you can see it's working fine, it's working perfectly, and it's working at the right voltage. Something like this Dremel is actually 130 watts. So let's connect that in and see what happens. Now that is on the first. Let's take the Dremel higher. Full max, it's turning but very slow, because that is taking most of the current. So if I wanted to test this Dremel, I would have to put a 150 watt light bulb in here. This toroid is actually 80 VA volt amps, which is kind of around, you know, 80 watts, something like this. I mean, it's not exact, but it's confusing to me. I wish they just put it as wattage, but yeah, it's roughly around about 80 watts. I think VA is a little lower than watts, but yeah. Now, as I was showing earlier on, this has two primary coils here. It's got 215 volt primary coils, so we don't want that. We're not going to use 115 volts here. It's 240 volts. Well, officially it says 230, but yeah, check your multimeter. It's 240. So what we need to do is each side the center side of each of the coils, just like tie that together, and it'll act as one coil, which is, you know, 240 volts. Of course, now I know the, you know, the primary windings. This is one coil, this is another, but I want to double check because I don't want to damage this thing. They are a little expensive. So blue gray is one, right? Blue gray is one, and that's the other. Okay, so all we need to do is you have brown live, blue neutral. Okay, we just shrink the tube. I'm done really. So let's plug this in. I've connected these clip things on the secondary coils, the output, and I've connected the input to that. So let's put that in, and that should be working. Of course, this is going to be 240 volts. Yep, 240. And here it should be AC 12 volts, 14 volts. That's good actually. I do want it a little higher than 12, even though it's probably because it's got no load on it, but then again, this provides 3 amps, so, you know, I don't think the voltage is going to go down too much. So yeah, around 12, 13 to 14 volts. Let's call it 13 volts output on each, which is fantastic. So while we're having a little fun, let's rectify one of the outputs. Normally with rectification, you need to use 4 diodes like this in that sort of configuration. However, you know, instead of this, you can also just get one of these, which is basically just a rectifier. 4 diodes in one little box, which is, you know, it's much neater and nicer, isn't it? You can see here you put AC in these 2 diagonal pins and you get a DC out of those diagonal pins. So it's just rectification. So I've plugged in the rectifier there and, you know, got direct current out of here. So let's connect a DC motor in here. As you'd expect, it just spins. Yeah, let's have some fun and see what happens when you connect it to AC, alternating current. Now AC, you can see what's happening there? It's not spinning, but it's changing directions 50 times a second. So obviously it's not going to turn. You can just like sit there and freaking vibrate. Now one thing I'm curious about are relay switches. Now relay switch basically is a coil operated switch. So you just like charge the coil and, you know, it will click the switch into place. Now I know that the coils are supposed to be DC. Ooh, nice and clicky. So basically the coil is activating and then pushing the contacts so they touch one end of the switch. So the switch is activated. Now let's connect this to AC. Like buzz its face off 50 times a second. Yeah, there you go. Okay, I'm having a bit too much fun with this transformer. This is my inner child. This is what I used to do when I was little, just aimlessly mess around for hours with components in front of me. So that's all for today. I'm gonna start building the circuit in the next video, so do stick around for that. Thanks so much for your likes, your shares. Do leave your thoughts in the comments below. Don't forget to check out my other videos and do subscribe for more. And don't forget to hit that bell icon because you won't be notified if you don't. Many thanks to all my patrons for supporting my channel, especially to my huge supporters and top tier patrons: Electron Skip UK, Axel Dominator, Robert Minis, Rich Corbut, Bohan Wayne Mitchell, and Chris Seblinski. Do see the video descriptions below to check out my patrons' websites and YouTube channels. Adios!